you're a freshman, it's as quickly as you can manage without making a mess. Okay. Hello, everyone. I'm Eric Lozette. I'm a professor in the Department of Science, and it's my great pleasure to introduce our speaker for the day. I just have a brief introductory blurb, so you have some context. So Dr. Dan Larremore is assistant professor in our department in the Biofrontiers Institute here at CU. He's also an affiliate of the Department of Applied Mathematics and a member of the external faculty at the Center for Community Disease Dynamics at the Harvard T.N. School of Public Health. His research develops mathematical methods using novel combinations of networks, analytical systems, and inference to solve problems in two main areas: infectious disease epidemiology and computational system science. Prior to joining CU, faculty, he was a mid-year fellow at Stanford Institute and a postdoctoral fellow at Harvard. He obtained his PhD in applied math from CU. And in 2022, he received the very prestigious Alan T. Waterman Award from the National Science Foundation, which is the National Science Foundation's most prestigious award for early career faculty. Pretty big deal. CU has 3 of those now in its entire history, puts us in the company of places like NYU and Duke and so on, and only Berkeley, Stanford, and a few other, regional universities are members. So please join me in welcoming.
Thank you so much for that kind introduction. I'm thrilled to be here. It's been 2 years since I got to yell at you for an hour during a colloquium. And 2 years ago, we talked mostly about rapid tests for COVID-19 and vaccine prioritization for COVID-19. And we're not going to talk about any of that today. Instead, we're going to be on a completely different topic, one which I think is super interesting, which is quantifying hierarchy and dynamics in US faculty hiring and retention. I want to start with a PSA, which is that as an academic, you're never alone. And I don't mean this as some mental health advocacy, although that's really important. I also don't mean it in terms of your collaborators, although they are also important. What I mean is that no matter where you go, some things follow you around. Where you did your PhD and your current affiliation. And I say this because anytime you apply for a grant, or you publish a paper or a book, anytime you talk to the news media or you apply for a job or a fellowship, these 2 things come with you. Where to do your PhD, and where are you currently a sitting faculty member? In fact, if you listen to Aaron's introduction, he performed one of the things that we as academics love to do, which is list each other's credentials. Okay, so why do we care about this? Well, it turns out that if you do a study where you either show people your affiliations when you submit a paper, or you don't show them your affiliations when you submit a paper, at least in the Journal of the American Medical Association, they found that reviewers were 28% more likely to recommend that the paper be accepted if you could see the credentials than if not. And they also gave higher ratings for the methods and other categories. And importantly, it's not just about acceptance, it's about error detection as well. There was no difference in the number of errors detected between the single blind and the double blind. So if you show your affiliation and you're prestigious, your paper is more likely to get in. And this has some consequences. I want to show you a result from a Proceedings of the National Academy of Sciences paper. This came out of our group in 2019. And what we're showing you here on the horizontal axis is the prestige of a computer science department, where over here on the left is the most prestigious. On the vertical axis is the number of publications that assistant professors wrote in the 10 years after they got hired. And what you can see is that as prestige increases up to the left, you have more and more papers that on average professors produce. On the pink axis over here are the logarithm of citations. And you can see that Citations as well tend to go up and up and up as prestige increases. So prestige seems to structure something interesting about the academic ecosystem. And this is something that's fascinated me and fascinated our research group for a number of years. But it's not just about publications or sort of the effects on individual careers. I want to make the case that this is also really important for communities, because if we take this person with their red and gold and we put them amongst a group of peers that also have a lot of red, gold, gray, blue, what happens if you come to this crowd and you want a job, you want to publish your paper, and you're not quite the same as they are? You want to get a job, but your credentials come from another institution and not one of the golds or the blues. If we lose this person because they don't quite fit in terms of their doctoral credentials, we lose their ideas, we lose their questions. We also lose whatever identities they carry along with them because they don't join this group. Instead, they go and take their talents elsewhere. So this talk is about who gets to join this group and really whether they stay. We're going to focus not so much on PhD students or master's students, but we're going to focus really on faculty. And I want to explain why. The premise of a lot of the work in our group is to study faculty because they shape the scientific ecosystem. You know, faculty individually, as we learned last week and the week before from Chris and Alessandro's talks, faculty make discoveries, they advance the science. But they also train students, and a huge number of you in the room today are students who are studying with professors. Faculty teach courses, they communicate science to the public, and they advocate for research priorities when they go to Washington and talk to their representatives. So essentially, everyone who gets a degree in anything has been shaped for better or for worse by a professor. And so it's important to ask, who are these people and where do they come from? So today's talk is really in two parts. Number one is the structure and dynamics of hiring and attrition in US academia. And the second, the topic which we should devote special attention to, is women on the tenure track, and in particular in computing. Okay, so let's dive in. I'm a little nervous, so I have some coffee to calm me down. Okay, first the data. You can't see it down here in the bottom right, but this says AARC, the Academic Analytics Research Center. They reached out to us after we published a few papers in the past and gave us 10 years of comprehensive faculty data. So what do I mean by that? Well, first of all, we have complete tenure track faculty rosters. So if you were listed as a professor in a department in the US at a PhD granting institution, you're in this data set. This covered 10 years, so the decade 2011 to 2020. And these were collected annually. So we have a sequence of snapshots. This covered all PhD granting US universities, all departments, which we clustered into 107 fields in 8 different domains. We also had each professor's PhD institution and the year that they got their PhD. And so in total, this is around 300,000 professors and 10,500 departments at 368 universities. So it's a lot. And importantly, it's comprehensive. A lot of studies in the systems in the past have looked at the top departments, whatever that means. Or they've looked only at institutions in the Midwest or other sort of selective groups. They might also have looked only at individual fields. But this data, thanks to the AARC, gave us an incredible bird's eye view of the system. And so 3 years ago, we set out to analyze it. Now, I should say, when I say we, what I really mean is Hunter Rothman. And Hunter, I think, is here in the black shirt. And so he'll be going through a lot of Hunter's results today. But Hunter, thank you, because it really makes the talk easier. Okay, so top line, we'll start out easy. So where are US faculty trained? This figure shows you these 8 domains in colors down below, and at the top, academia in blue. And the open areas show you people who have a US doctorate. The little shaded slivers on the left show you people who don't have a doctorate but are professors. And over here on the right in the hatch, these are people with doctorates but not from the US. So about 93% of professors have a PhD or some equivalent. But there's variation. So 1% lack a PhD in the social sciences versus 19% in the humanities. So now I'm going to ask for a little audience participation. What fields do you think have the lowest restrictions on? Hunter, you're not allowed to answer this. What fields do you think there are that don't require a PhD?
Art.
Business? I heard arts. Any other guesses? Music. These are great guesses. So here we can see the percentage of faculty without a doctorate in a bunch of different fields. And we're going to see a lot of plots like this. So let me just go through and explain. We have some vertical axes. The first dot here is going to be in blue. This shows you the stat for all of academia. Then we're going to see columns of dots. And each one of these corresponds to one of the domains that we've listed over here. Each one of the colored circles is a field. So this is one of the 107 fields. And the big gray dot tells you the average over the whole domain. So you can see here, urban planning, architecture, theater, art history, great guess, music, nursing. These are fields where over 10% of faculty don't have PhDs. You can see that actually in most fields, you really got to have a PhD. And on average, in each of the domains in gray, you got to have a PhD. Okay, so great guesses. We'll see a lot more plots like this. So where do US faculty come from? It turns out that 11% of faculty have non-US doctorates. They come from 123 different countries. But again, we see variation. Only 2% of education professors have non-US doctorates versus 19% in the natural sciences. And if you know any education professors or natural sciences professors, I'm sure you're starting to think about reasons why this might be the case. Okay, this is why I think it's so interesting. Because you see a stat like this and you're immediately thinking like, I wonder why, what would cause that? What would drive that? Okay, if you're a nerd snake by this, then you should maybe think about doing some research in this exciting area. Okay. So let's drive in a little bit more. Where do faculty trained abroad actually come from? Which specific countries? What we're going to do again is separate by these domains. I'm going to show you these 8 different bar charts. So for each one of these 8 domains, we have 6 different continents listed. And I shaded within the Europe and the North America bars areas for the United Kingdom alone and for Canada alone. And there are a lot of interesting patterns here. You can tell a lot of different stories, but I want to highlight just one. So fully 35.5% of US professors who got their doctorates abroad come from the UK or Canada. But just 5.5% were trained in all of Africa or the Americas, excluding Canada, and of course the US combined. So you could ask a question outside of representation alone. Does this matter? Like, are there consequences? And for this, we're going to have to think like demographers. So what would a demographer do? They might be interested in something called attrition, where they're looking at longitudinal data, the same system over time. And what we're going to ask is whether attrition, whether or not you leave the academy, varies by your location of training. So you quantify this via what we call a risk calculation. It's pretty straightforward, but we'll just walk through one example. I calculate risk by counting the number of events that occur, here attrition events, and I divide by the total number of people who are at risk. So here's a little example. Let's imagine that in 2011, I have 4 professors in the department. When I look at the next snapshot, I have 5 professors, but actually 2 of them were new professors and 1 left. In the next year, I see a total of 3 professors, but that's because 2 left and none joined. So I can write out the number of events as 1 event, 2 events of attrition, and the number at risk were 4 professors in this year and 5 in this year. So in total, I had 3 events and 9 person years at risk. And so I say that I have an annual per capita risk of, you're gonna have to do the math in your head because of Zoom, 1/3. Okay. So a risk ratio is exactly what it sounds like. It's a ratio of 2 risks. Pretty profound stuff. It's the risk in population A over the risk in population B. And so if this is one population, and I have some other population where, again, I have some new hires in different colors, but I also have some attrition events, I can calculate a risk here of 5/11. And so the risk ratio is, you take your 3/9, you divide by your 5/11, and you get 33/45. Now, anybody who's taken a math class knows what you can do with a fraction like 33/45. What can you do with this fraction? If you divide by 3, you can reduce it, right? So you pull a 3 out of the top, you pull a 3 out of the bottom, and you cancel those, and you get 11/15. And this is proof, I'm telling you right now, academics are pushing cancel culture. If you give this to me, you're gonna get marked down. You gotta get to 11/15. Okay. There has to be So how do we interpret this? This is the risk of A over the risk of B. So if the numerator is larger, then group A has the higher risk. If the numerator or if the denominator is larger, then group B has a higher risk. And if it's 1, then they have the same risk. And so for any data, we're going to ask whether or not this number is statistically distinguishable from 1. So here's what we find. On the left, Canada and UK professors versus US trained professors. And we're looking at that risk ratio by doctoral origin. So the one line is in bold. And what you can see is that there are a lot of X's, and every time you see an X, that's not statistically significant. Every time you see a circle that is statistically significant, meaning we can differentiate that number from 1. And what you see here is that for professors trained in Canada or the UK, there's actually a slightly lower risk of attrition than for professors trained in the US. But not so for those professors trained in other countries than Canada, UK, and the US. What you can see here is that not for every field, but for many fields, there is not only significant, but substantially higher attrition risk overall in academia, in all 8 domains, and in a large number of different fields. So what we're going to argue here is that this really does matter where you train. Academia is losing these professors at a differentially higher rate than these professors. That's important if you're interested in not only equity and representation at hiring, but also equity and representation over time. So where do US trained professors come from? We're going to look at this on a different graph. So along the horizontal axis here, I'm showing you the percent of universities from 0 to, it's hidden over here, but 100. And on the vertical axis, we're going to plot the percent of US trained faculty who are produced by an individual institution. So the tallest bar here turns out to be University of California, Berkeley, who produces around 3.5% of all US professors. And it turns out that I can group these, and 8 institutions produce this blue chunk. That's 20% of professors. Another 13 institutions produce 20% of professors. 20 produce 20%. 38 produce 20%. And the last 28, or the last 20% are produced by 308 institutions. So if you've ever heard of an 80-20 rule, this is sometimes called a Pareto Rule or Pareto Principle. Academic hiring within the US follows this rule. In total, 80% of faculty come from just 20.4% of institutions. That's 79 institutions, supplying 80% of US trained faculty. It's wild. Okay, another way of putting this is that over 1 in 8 faculty were trained at just 5 places: Berkeley, Harvard, Michigan, Stanford, or Wisconsin. If you're me and you're working in a public institution, you're a little bit excited here. Because when I think about prestigious institution, I typically think about your Harvards and your Stanfords and your MITs. But this is pretty interesting. Berkeley, Michigan, Wisconsin, 3 of the top 5. Okay. Nevertheless, these 5 train more US faculty, that's around 14%, than all non-US doctoral programs combined. That's 11%. So again, we see this substantial inequality. Okay, so this is looking at academia overall. Let's drill into particular fields. Again, what I'm going to show you is gray curves are for overall domains, and each individual colored line is for a particular field. Now, these are called Lorenz curves. What I do is I back up universities and I accumulate a bigger set of universities from 0% of them over to 100%. And as I do so, I count how many professors do I have in my stack. And because I've sorted them, what we're going to do is see how quickly the percentage of US trained faculty accumulates as I include more institutions. If every institution produced the same percentage of faculty, we would just track along this line, because the rise over run as we added more and more institutions into our sample would just be flat. What you can see here is that if you connect across this grid point at 20% of institutions and 80% of faculty, you're satisfying that Pareto principle. And not all domains show this. So humanities is a little bit worse than the Pareto principle. Education, a little bit less. But you can see that in general, all of these are showing substantial inequality, even when we go away from all of academia and drill down into specific fields or particular domains. So I want to look at this over time because this gets even more interesting. What we're going to do is take each of those Lorenz curves and just turn it into a single number called the Genie coefficient. And the Genie coefficient is a way of quantifying inequality in production in a system. You may have heard the Genie coefficient used when people talk about income inequality in the US. So the Gini coefficient for US income inequality is around 0.56, depending on how you calculate it. What's the Gini coefficient for faculty production? Between 0.6 and 0.8, depending on which domain you look at. So one way of thinking about this is that US faculty production is more unequal than income inequality in the US. But an important point is that these are not changing over time. Over the decade that we're looking at, these Gini coefficients appear to be pretty flat. But look what happens if I separate out and look at the Gini coefficients only for new faculty versus sitting faculty. In what we're calling tadpole plots, you can see that the new faculty are uniformly lower than their corresponding matched existing faculty across all the domains you look at and across all the fields. So faculty production is less unequal for new faculty and more unequal for sitting faculty. So you're probably thinking, like, what gives? Have there been some big changes in how professors are hired? As it turns out, this isn't the case. What we can do again is look at attrition, which professors are leaving year by year, and via logistic regression, ask, can we predict whether or not a professor is going to leave or not by looking at the production rank of the institution? So this is what we're showing here. More faculty produced is over on the left, fewer faculty produced over on the right. And these curves show you the average annual attrition risk in the logistic regression fits. But what you can see here is that it's always lower over on the left. Attrition risk is lower on the left than on the right. Another way of doing this is to compare where you intersect the left axis with the right axis. And what you can see is that faculty with the least elite PhDs show nearly 2 times the attrition rates of their colleagues with the most elite PhDs. What does this mean? It means that there's substantial inequality in faculty hiring and that this inequality is exacerbated by attrition. So if you're thinking about dynamics over time, what this means is that this process is making cohorts less diverse by doctoral origin as they age. Okay, so a couple reflections here. If we had examined just one of these plots by itself, we would have led to an incorrect understanding. Like, you can't get it from this plot alone. You can't get it from this plot alone. You can't quite get it from this plot alone. You have to put all of these together, and really the longitudinal data are critical to understanding the system. Snapshots won't do. And this is one of the big advances, although subtle, in this work over previous works. So I want to talk about now prestige in faculty hiring. I want to think a little bit more about this person. Because let's say that I don't know this person. I don't even know what their face looks like. But I do know that they have this particular credential. So there are 2 really interesting theoretical underpinnings, and one of them comes from somebody who has one of the most prestigious credentials you could think of, a Nobel Prize. Okay, it's a Nobel Prize in econ, which some people will say is technically not a Nobel Prize. It's like named after the Nobel Prize. But we're not going to litigate that. Michael Spence won the Nobel Prize in 2001 for his 1978 paper, along with Akerlof and Stiglitz, and it was called Job Market Signaling. And I put the table of contents here because there's a particular bit that I want you to look at. Section 2 right here is called Hiring as Investment Under Uncertainty. And Spence's big insight was that if you're looking at a stack of resumes, you don't have time to work with every single one of these people for like 2 years and learn who's really the best candidate. Instead, you have a lot of uncertainty. You don't know that much about them. You can at best interview them. Maybe they do like an internship or something, but there's a lot of uncertainty there. And so what do we do instead? We rely on signals. Now, I think this is a really exciting topic. Put a little clock down in the corner to remind myself to shut up and move on. But the key understanding in job market signaling is that if the signal, like a credential, is easier for people to get when they have some attribute that's correlated with the thing you want, then the signal is useful. And so a PhD or a master's degree is that kind of signal if you're interested in hiring somebody with research abilities, right? Okay, so this was job market signaling. It was then built on by Joel Podolny. He doesn't have a Nobel, but he's a VP at Apple. I think he's doing just fine. He wrote a paper called A Status-Based Model of Market Competition. And this kind of takes some of the ideas from Spence and then brings in this idea of status and some self-reinforcing processes that allow people to attach a certain value to things like a particular doctoral credential. In more recent years, people have given a sort of interesting definition for prestige, which sort of comes out of this work, which is freely conferred deference. So in social hierarchies where prestige is at play, you don't have a pecking order where some birds or some humans are pecking each other and enforcing the hierarchy through dominance interactions. Instead, prestige is freely conferred deference. So when you hear something like, well, you know, she's a professor at Yale, or he's a Harvard man, these kinds of things, when they're spoken, often give the people about whom we're talking some extra credibility, some deference. Okay, so enough about that. The theory is super interesting. What about the data? What we're going to look at are faculty hiring networks. And this is a picture from a 2015 paper, a study led by Aaron. This is showing you a faculty hiring network of flows of PhDs out of MIT into these other institutions. And we've highlighted the ones out of MIT just because we want to highlight them. But of course, you can see that in the background, there's this tangled web of exchange of PhDs going into faculty jobs. So we're going to have three premises when we analyze these. Number one is that each hiring committee, when they're deciding on one of these individual flows, wants to hire the best. So what does the best mean? I don't know, but it definitely doesn't mean like number 50 out of 200. Right? If you have a big stack of resumes, you're never looking for like the most median candidate. You're looking for the best candidate, whatever that means for you. What this means is that each hire going from institution U to institution B is an implicit endorsement of institution U by institution B. And that's one endorsement. So if we look at the whole network, this is going to reveal the collective mutual endorsement, which we hope to learn from. Now, this isn't prestige directly, but what we're going to argue is that this is going to tell us about sort of the shadow that prestige casts across academic hiring. So what we can do is then learn that prestige hierarchy by trying to find a particular ranking of these institutions. So how do we go from a network to a ranking? How do we infer prestige from a network? In a perfectly strict social hierarchy, no university would ever hire from someone less prestigious, right? You would only source your faculty from places that you think are equal to your level or ideally even better. So given such a hypothetical network, we could therefore find some kind of ordering so that all of the flows go down the network and zero of the hiring flows go up. It would be a perfect strict hierarchy. So for real networks, what we can do is infer prestige by finding a ranking that gets as close to a strict hierarchy as possible based on the real hiring flows. Now I know what you're thinking. You're thinking there are n factorial possible orderings at n universities. So option one might be to search this huge space by using some clever MCMC where you're kind of wandering around the space of rankings, swapping which node is in which place until you find a good ordering, or use a convex approximation and some sparse linear algebra to get there faster. And of course, we're going to do option two. We're going to use a method called spring rank that we published in 2018. And we like this because it essentially accomplishes what we want to do here, but it's really fast. Okay. Now there's a little bit of a puzzle because if I tell you that a prestigious university is prestigious because it hires from more prestigious universities, it might feel to you like we're sort of chasing our tail. Because how do you know that those other universities are more prestigious? Because like, how did they get their prestige? They hired from them. It feels like circular reasoning. But we're computer scientists. We know that's not the case. This isn't circular, it's merely recursive. So this is actually a recursive definition of prestige. And if you're familiar with the PageRank algorithm, the way that we rank web pages, you know that an influential web page is influential because it's pointed to by other influential web pages. And we recurse and recurse and recurse, and we get some measure of influence. Here we're doing it by prestige using this particular functional form. So what happens when we apply this kind of method to a faculty hiring networks? Instead of ordering things linearly, we're going to wrap them around the clock. And here's what something looks like for computer science faculty hiring. So let me explain this diagram. Up here at 1201, I put the most prestigious institution and wrapped around all the way to 1159, the least prestigious institution. The width of the bars in such a diagram tells you about the number of faculty that this institution produces. And I've colored the flows that connect one institution to another. If the flow is going down the hierarchy, I've colored it blue, and if it's going up the hierarchy, I've colored it red. And if you look at this and you say, I'm calling BS because that's entirely blue or almost entirely blue. Your eyes don't deceive you. These really are strict social hierarchies. A way of thinking about this is that these have low upward mobility. So if we looked at the network for classics, we would see only 5% upward mobility. In econ and finance, 6%, art history and stats, 7%. For those in the room who are in these fields, 9% in mathematics, 12% in computer science, 14% in information science. And if you're thinking like, oh, 14%, not bad information science, 14% is like 1 in 7. So 1 in 7 professors can traverse up this steep hierarchy of prestige, 6 and 7 cannot. So it's not just that there's low upward mobility, it's that we also see some interesting systematic patterns. So there are 1,070 possible top 10 slots for 107 fields. Turns out that 248 of those slots, so nearly a quarter of them, are taken up by just 5 institutions. In contrast, fully 252 institutions have 0 top 10 slots. So this is nearly 2/3 of institutions. We can also do pairwise correlations between the individual fields. And that's what this chart is showing. Here you can see a row or a column for every individual field. And we put a pixel that's colored depending on how correlated the rankings are in those fields. So this sort of medium teal color is neutral. And the more yellow it gets, the more correlated. If you see these midnight shades, these are anti-correlated, so opposite rankings. And essentially all, except for 116 of these 12,000 pixels are positive. Pathology has the least correlated rankings with any other field. I have no idea why. It's a killer stat. Okay. Good. Okay, so there's some implications here. And I think these are really important for how we hire faculty and how we select our peers, essentially, how we select our colleagues. So if you take production inequality and these steep prestige hierarchies, and you note that the average US trained professor moves 18% of the way down the prestige hierarchy when they get their faculty job, this means that the typical professor can expect to supervise 2.5 times fewer future faculty than their PhD advisor did. Why? The PhD advisor was productive, you move down, you supervise fewer people because you generally produce fewer faculty. So this is pretty wild. This is kind of an interesting network result. What else can we say? We can also look at the structure of these networks from another lens, which is called the core and periphery lens. So in the structure of these networks, the prestigious institutions sit toward the middle of the networks, closer to all the others. And the networks have no particular geometry. So instead, what we're going to do is look at each node in the network and ask, how many hops does it take for me to get from this node to another node? How many from this node to some other node? I'm going to do that for all the different nodes and then average them. So I know how close on average is this one focal node to all the others. And when we do that and we sort by university prestige, what we can see is that that mean distance divided by the diameter, so that things normalize to 1, is smaller when you're high prestige, larger when you're low prestige. So the high prestige institutions in the structure of the faculty network are topologically closer to all the other institutions than the low prestige institutions on the periphery. So this plus the production and prestige pattern means that you essentially have a core of universities that have a mutual exchange of graduates. And those core universities export their faculty by and large to the periphery. But the periphery rarely exports faculty back to the core. Instead, they just typically import. Okay. So if you think this stuff is cool and you like interactive data visualizations, Hunter has put together some really cool visualizations. I'll show this at the end as well, but you can explore these circular plots, and you can also look at the rankings, compare against your friend's school, and so on. So I want to talk about gender inequality because this topic is really important, especially in computing, where we know that we're essentially always competing with physics and engineering for the worst. So here's what things look like over the decade, sorted out by the domains. From 2011 to 2020, women's representation significantly increased in academia overall, all 8 domains, and 80 out of 107 fields. The remaining, except for 1, were flat, and only 1 was there a decrease in women's representation. That was in nursing. So it looks like progress. And I want to now convince you that that's not actually great progress. Why do I say this? We're going to do the same thing with the tadpole plots. We're going to look at new hires on the left of the tadpole plots and attritions on the right of the tadpole plots. And it looks like new hires, we have higher women's representation than among attritions. Now, these are all cause attritions. That includes retirement, it includes death, but also includes leaving our sample for a wonderful job in industry. Okay, so this is interesting. More women are coming in, more men are leaving. We see these systematic patterns across fields. But this is actually explained when we look at the demographic curves within the fields. So here I'm plotting career age on the horizontal axis. This is the number of years since people got their doctorate. And then we're looking on the vertical axis at women's representation. And what you can see is that why the demographic curves show why we see this pattern in the middle plot. Essentially, in every one of these domains, you slide farther and farther away from parity for cohorts hired longer and longer into the past. So this looks like progress, but I think it's really driven by retirement. These folks are retiring, and the retiring folks tend to be more likely to be men than the people who are being hired. Importantly, there are no upward trends in women's representation among new faculty in and of themselves over our decade in any field. Furthermore, new hires remain predominantly men in 75 out of 170 fields, particularly in STEM. I want to call your attention to where these curves intersect our axis. A lot of these curves are substantially away from parity. So there's a warning here, which is that without continued efforts toward parity in hiring, these changes that seem like they're encouraging are likely to plateau. Okay, I want to unpack this one step further by zooming in on this plot, really zooming in. I told you that hiring of new hires was flat over a decade. But the perceptive among you will notice that this is sloping down. All of these are sloping down. So shouldn't these be flat if new hires were actually flat? What we must be seeing here is some effect of attrition of junior faculty. So let's dive into that a little bit more. People have studied this topic of the leaky pipeline, where at higher and higher levels of seniority, there are fewer and fewer women. The literature is kind of a mess. Over here on the left, there's some papers that find that there are no differences by gender. Over here on the right are papers that find, yes, there are differences by gender. And in the middle, a group that we'll just call it's complicated. But there are limitations. So most of these studies are done, again, at a single institution or a small group of institutions, or at a single point in time, or on a specific academic field or a group of fields. But we have all the data. So we can go far beyond this and test new hypotheses and see what could possibly explain a literature so conflicting as this. So what we're going to do is take attrition risk again and stratify it by career age. So I'm going to ask, what's the attrition risk for brand new professors, for 5-year-old professors? And you know what I mean, 5 years since PhD. So the average attrition risk here is around 5%. And look what happens when I put all those professors here. What you can see here is this beautiful curve in the data. Being an assistant professor is stressful. People leave. Associate professors like to hang around. Full professors, especially after years 25, start to retire. So you can clearly see the sort of up or out filter at tenure, years 3 to 6, and the gradual onset of retirement among faculty who have been here for a bit longer. So watch what happens when we separate this and make separate curves for men and for women. The tenure and retirement curves persist, but women leave academia at higher per capita rates for every career age. Every single one of these teal points is above its counterpart grade. Here's what happens when we also include promotion and when we drill down into particular fields. So these are the results from a regression analysis where we control for a lot of different variables, including productivity, prestige, and so on. What you can see is that the patterns are more complicated. So the top line in academia, again, assistant professors are more likely to, attrition is higher for women assistant professors, associate professors, and full professors, because these points teal are teal, and they're to the right of this neutral line. If we look at promotion overall, you can see that the point is to the left, and we've colored it black because men are significantly more likely to be promoted at the associate stage and to be promoted at the full stage. Drilling down into individual domains, you can see that this pattern generally is the case, that women are more likely to lead and men are more likely to be promoted. But there are a lot of domains where there is not a statistically significant difference. These are the open circles. And actually what we see is that in engineering, attritions are more likely to be men than women. I have no idea why. This will be really interesting to dig into and find out. So the academia level patterns hold broadly, but not always within the domains of study. And we also see some interesting patterns for promotion. Okay, so why? So if you're a physicist and you're like studying cold atoms, you can never just ask the atoms what's going on. But because we're talking about faculty here, we can just reach out to them and ask, like, why did you leave? What caused you to take another job? So we conducted a survey, and we got around 10,000 responses from current and former US faculty, sampled from that previous data set. They covered 325 institutions, 25 fields, and the sample was collected in fall of 2021. Maybe some of you filled out the survey. If you did, thank you so much. What we asked were which stressors and what forces, either positive or negative, caused you to leave your job. But here's what we found. We're just gonna kind of scope out what this plot is about to show us. Number one, we're gonna look at overall stress on the left, and we're gonna divide it out into 4 categories based on the literature: research pressures, departmental support, work-life balance, and workplace culture. Gray dots are gonna be for men, teal dots are gonna be for women, and we're gonna divide the professors into 4 groups. Current professors, those who left academia, those who switched between institutions in academia, and those who retired. And we're asking them about their job before they left, switched, or retired. Okay, so what do we see? First of all, overall, women report more stress than men across the board. And this really lines up with a lot of the literature. So you can see that across all 4 groups, the teal is to the right of the gray. The mean stress score, in other words, is higher for women. Let's drill down into those 4 categories. What we see is that research pressures and departmental support are in general, oh, I've lost my middle lines. In general, farther to the right than the others. So these are the categories that are the most stressful. Perhaps unsurprisingly, the largest gap between men and women occurs in workplace culture. So what we can also do here, because we're actually asking people about their experiences, is asking them about their identities as well. So we're going to stratify this plot between white faculty and non-white faculty, and you'll notice a pattern here as well. In the light grays, white men, dark gray, non-white men, light teal, white women, dark teal, non-white women. And I'm putting a little line here just to call your attention to this trend that we see in some, but not all of the plots. Namely that white men tend to be over here on the left with lower stress, non-white women over here on the right with the highest stress. So these patterns I think are important because these kinds of stresses are, as we're going to see, be pushing people out of academia. And if we're actually interested in diversity and equity in the academy, we need not focus only on hiring, but we also need to think about these stresses and all the things that happen within the department's culture after hiring as well. Okay, let's look at some things over time. Again, we have our 4 categories of stresses. These are embodied in these kind of different curves. I'll call your attention to just a couple of key points. Number one is that the 4 different categories are essentially in, reasonable stalemate competition for the stresses of men, but not so for women. Look, for junior faculty, you can see that work-life balance is really hard. And for women in general, over the course of their careers, but especially for senior women, workplace culture is a real driver of stress. Now, this is interesting. We asked people about, were you pushed out of the academy or were you pulled out? Because we know that there are fantastic jobs outside of the academy. There are really interesting opportunities. So sometimes you just get the right opportunity and you get pulled out. Sometimes you want to switch institutions within the academy. And so you get pulled out. And what you'll notice is that in general, men who switched report more polls at women who switched, men who left, more polls at women who left, and swapsy ways over here on pushes. Men are more likely to leave due to a poll, women are more likely to leave due to a push. So there's some implications here. Women are more likely to leave and less likely to be promoted, and we see clear gendered experiences of workplace culture. So number one, we need to analyze both these large-scale data sets, but also get these rich, detailed surveys and interview studies to understand why people leave. Number two, there's value in quantifying these inequalities, but only if we then actually take some action, specifically on improving, in this case, workplace culture. Finally, retention is complicated and it's nuanced. We need to actually listen to people's responses and address the specific reasons that they bring up, particularly if these are groups that are historically excluded and who we hope to include in the academy. So a lot of this work was driven by name-based gender classification, and I want to highlight some methodological things that we've done in this area. A lot of existing tools will allow you to take a name like Dan and say, that's probably a guy. But these existing tools are either pay to play or freemium, and they also aren't transparent. Importantly, a lot of these tools don't sort of come out and say what I think should be pretty obvious, which is that names don't actually have genders. Cultures associate names and genders. So our approach here was to take a name and to try to generate an estimate of cultural consensus from huge amounts of data where we look at names and declared sex at birth across a huge number of countries, contexts, and years. What we try to estimate is that cultural consensus of a name's association to a woman or man gender. And we do that with some equations. We're not going to talk about these, but suffice it to say that this is, again, not circular, but recursive, and we can solve this one with a nice EN algorithm. This work is out there in case you might be interested in using this in your research. You can pip install it, you can import it easily. And as Chris mentioned last time during his talk, it's really important that we create these sort of production quality tools that other people can use. We have a Python package, open source code, and importantly, open data if others want to build on this. Okay. In the interest of time, I'm going to skip these slides. I want to highlight one other result, which comes specifically from computing. Here, we were interested in understanding subfields in computing and the interactions between subfields, prestige, and gender. So what we did was we took the tenure track professors in computing. We linked them to their publications. And then we used a semi-supervised topic model to understand professors' subfields. So here, for example, you can see Jim Martin in the second column, Laysha Palin in the far right column, and what the topic model thinks when it divides them across these 8 different subfields in computing. Okay. So what we can then do is look at all of these professors and we can sort them by prestige and ask whether or not particular subfields tend to be studied at higher or lower prestige institutions. So here's what we find. Some topics are more prestige concentrated at higher prestige institutions than at lower prestige institutions. Now, all of these you can see, we have a higher density of professors over on the left than on the right. That's because there are more professors over here on the left because these departments tend to be larger. But you'll notice that there's a difference between these curves. So theory, PL, machine learning systems, scientific computing, these are all in this kind of high group here. HCI, interdisciplinary computing, and software engineering tend to be relatively more concentrated at the lower prestige institutions. Now look at what happens when we take these subfields and we look at their composition by women's representation. Here you can see the subfield fraction of women on the horizontal axis and the fraction of professors at the top 50 institutions from the plot on the left. You can see a pretty clear negative correlation here, which is to say that women's representation is negatively correlated by prestige when we separate out into these subfields. If you again look at these subfields, you can see that over time, women's representation in the different subfields has been changing, but there's kind of a cluster of subfields down here and a cluster up here. These are an inexact map, with the exception of which one? I think ML? No, systems, with these groups over here on the left. But if you look at where this cluster of fields gets to relative to the other, you can sort of do a calculation and say that theory PL systems and scientific computing are around 20 years behind HCI, interdisciplinary computing, software engineering, and machine learning. So all of this is to say that there are interactions in the system between prestige, the topic you study, and gender. And if you're interested in changing representation within the academy, you've got to understand these structures and how prestige affects representation, topic, and hiring all at once. Okay, so let me sum up. The first story here was really about inequality. Most US faculty come from a small number of institutions, and there's a strong hierarchy of prestige. There's little upward mobility, like 5% move up in classics, 6% in econ. Women's representation is increasing, but due to efforts of generations past, we're forecasting a slow plateau across these domains. And we talked about attrition. So we found that there was higher attrition for those who were self-hires, so employed by their PhD institution. I didn't tell you about that, you got to see the paper. People who are trained outside the US, UK, and Canada, and people who are graduating from less prestigious institutions. We also found that there was substantially higher per capita annual attrition for women at every career age and stage. And that inequalities are often instantiated during hiring, but they're really exacerbated by attrition. And finally, some notes on computing. Number one, working with longitudinal data provides a lot of texture and surprises. Cross-sectional analyses are valuable, but they're really limited. We also really like recursion. We like relaxation and convexity, EM algorithms, open data, open code, and equity. These are all things that I think we need more of in computing. And finally, computing subfields are unequally distributed by prestige and correlated with women's representation. So if we want to change our own field, I think these are things we need to think about. If you're interested in reading more, here are 4 papers. The first one on hierarchy and dynamics in faculty came out in Nature yesterday. The one on gender and retention patterns is under review now. No preprint available quite yet. One on subfield prestige and gender inequality in computing will come out in the communications to the ACM in December. And the open source approach to name-based gender classification is under review, but is on the archive. Of course, I need to thank all of these folks who have provided funding to the lab. But more than the funding, I want to thank the actual people in the lab. So this is a graph of our collaboration network. Each one of the blue dots is a paper written by someone in the lab. And each one of the green dots is a collaborator on that paper. And the people here in pink are current members of the lab, and I just want to shout them out because I get a chance to. So number one, this one's Hunter. Hunter did all that work on faculty hiring that I shouted out at the beginning. Nice work, Hunter. Nick LaVerge was the one who did the work on computing in particular and looking at that subfield stratification. Thank you, Nick. Ian Van Buskirk was the one who wrote down, coded up, and wrangled all the data for name-based gender classification. Thank you, Ian. Katie Spoon is the one who's been looking at gendered patterns of retention among faculty. Thank you, Katie. Katie has been working with 2 research assistants to look into the actual text response to see what people said when we asked them why they left. That's Joanna Mendy and Maria Martinez. Sam Jung has also been working in the group. And all of these people together form our crew on computational social science, along with some of our lab alumni, Kay Wooten and Lee. Of course, we also had work from some people who graduated far in the past, like Katie Younglove and Sunil Soti. But we also have a group working on networks and inference. So Suchi Yen is over here working on networks and creating some really nice software products. He's joined by Afra, Aaron, and Pasna. And then, of course, we have a lovely group on computational epidemiology. So Eric is our PhD graduate. He's now working for Invitae on Google. Suchi Lula is at the University of Utah now. Kate Bubar, of course, did all the work that I talked about 2 years ago on vaccine prioritization. Casey Middleton is working on testing now. So this is a really fantastic group, and I absolutely love working with them. I also love the fact that they'll indulge me in making these little Harry Potter gifts. But you'll notice that there's a gap here. I really want to call attention to one other person who's in the group. He's not really in the group, but he's kind of in the group. And that's Aaron. Aaron, with his fantastic labor background, has been a really great collaborator, particularly in this amazing cluster of computational social science. And it's great to have wonderful mentors like Aaron, who not only introduce you at your talks, but also support you and help give you good advice throughout. So thank you. If you want to learn more, you can check out the website. And if there's time, I'd love to answer any questions. Thank you.
Mine was about journals, so doing an equivalent analysis of where people publish and an equivalent reputation rank of journals. Do you think that there would be also equivalent patterns, like prestigious people publish in prestigious journals and it's all downhill from there?
So the question that I'll repeat for Zoom is like, what about journals? Do prestigious people publish in prestigious journals? So I think that's a really interesting question, but you're going to get the obvious result, which is yes. Prestigious journals tend to publish prestigious research by prestigious people. That's why they're prestigious. But I think the interesting adjacent question is, why are some journals more prestigious than others? Why do they accumulate that prestige and how do they do it? Like, what's the mechanism? So what we've been talking about around the lab is this idea of what we're calling prestige mutualism, right? Like, how does a journal like the newly advanced or newly released Science Advances, when did that start? 2015, I think. The Science Advances started in 2015. How did it become prestigious? It did so essentially mutualistically by publishing highly prestigious work from prestigious authors, and then using that to create a feedback loop that attracts people's best work. And so I think this idea of prestige mutualism is interesting, but what we need is a way of comparing people's preferences for publications directly, instead of just inferring them from who publishes in them. And so one thing that we're looking at now, and this is actually work led by Ian, is actually allowing people to compare pairwise journals. Like, would you rather have this paper or this paper as your next one on your CV? And by learning from those pairwise comparisons, we can infer a separate hierarchy for prestigious journals and see how these exchange rates, the currencies, have a lot of value in some fields, but essentially no value in other fields. Like an American Journal of Sociology publication has very little value to most people in here, and yet it's highly prized in other fields. Okay.
Do you have the information of the number of people in faculty graduating from Colorado Boulder?
Do we have info from CU Boulder? Yes, I should have known that this question was coming. I would encourage you to go to the lab website and you can explore the visualizations there. What I can say is that depending on the ranking that you look at, we're ranked anywhere between like 15th down to like 50th or 60th, and it depends a lot on the field.
Great talk, thank you. So my question is about, like, you have all of this data about faculty attrition, and obviously, like, every university is looking to kind of limit this or reverse a bad trend there. But you can actually see in your data, like, who's reduced their attrition rates. And I was wondering, like, have you identified these universities and like asked them basically, like, what have you done that actually worked here? And like, how do you contrast that against everyone else?
So the question was, have you looked at individual universities and been able to see which universities are sort of doing better when it comes to attrition than others? Nope. No, we haven't. It's such a good question. We haven't done that. Hunter, what are you doing today? No, Hunter gets a day off. Yeah.
So we have this data that I will be really for the long period. Can we do something to change this with the research?
I hope so. I mean, I hope we can do something to change this. Because I think that, well, so it depends on what you're looking at. So I think we can do things to change representation. I'm less optimistic about our ability to change things like the structure of prestige. So there's this beautiful book, I think it was written in 1958. It's called The Academic Marketplace. It's a book by these sociologists, Kaplow and McGee. It's brilliant. I mean, it's full of amazing quotations. But essentially what they say is we went out to study faculty hiring in the 1950s, and we couldn't explain what was going on without prestige. I mean, that was in the 1950s. That's like 20th century stuff. That's ancient, and yet these patterns are self-reproducing, right? The top institutions then are the same as the top institutions now. So I think understanding those feedback loops and then sort of unpacking them is probably an important next step, but I wouldn't say I'm optimistic.
So I was always interested in that we value what we measure. And I felt the real challenge would be to measure what we value. And of the PS department, there discussion over years, for example, should we count when you came up for some yearly evaluation or promotion, should we count the number of publications or the quality of publications? And obviously, counting the number of publications is we measure, we value what we measure because we measure. But I mean, there were discussions, and sort of my personal belief, one should at least also look into this. Should we first determine what we value, and then we try to come up with measures to do so. So, is all your data having some notion of that there are, you have an infinite number of beautiful graphs, lots of data, but are they sort of a little bit caught also in this distinction?
Sure. Well, so one comment I'll make about value is that I think there's a, je ne sais quoi about quality, right? You pick up a paper and you read it in depth and you put it down, you just think, God, that was what a fantastic paper. But that takes reading the paper. And so typically what people do, is they'll look at where you publish and try and think about that as, again, from the suspense point of view, as a signal of the quality, a proxy of the quality instead of the actual quality. The thing is, assessing quality is really hard. And if you have 150 faculty applicants in front of you, and each one has written 20 papers, good luck, right? Like you'll never read all of them. So I think we really have a problem here, because if we really want to assess something like quality of research, that's super hard.
But I think academia is here for doing tackling super hard questions. So I think that
I agree with it. I agree with it. And yet, having sat on like grant review committees and fellowship review committees, I think it's harder than simply we need to put in more time to evaluate each other. But I take your point. We have time for one more. Claire.
Just that statistic that from the PhD granting institution, people go down by 18%. Is that just percentage computed over these 368 institutions, or is it weighted by number of faculty positions for those institutions? Right. So are you just looking at 80% in a ranking, or is it weighted by the head count in those institutions?
Yeah, so I'm going to indulge and grab a little chalk to answer this. So you have some kind of ranking that goes from 0th percentile up to the very top. And you see these arcs. So somebody gets a job at like 80th percentile and move to 60th. And somebody else moves down, and the occasional person moves up. And so all we're going to do is take these lengths, and most of them are negative, some are positive, and just average them. So we're getting an average over all of those movements, and that average over all of academia is the minus 0.1.
And the percentile is computed just simply by ordering all the institutions, not weighting them by the number of posts.
Yes, that's right. The way that we get these ranks, so basically to take the faculty hiring network, spring rank it to get the ordering of the nodes, and then convert that to a percentile from 0 to 100. Thanks, Dan.
Dan, you had one question. I'll assume that's Leisha said, first of all, great talk. She said, do you know to what extent grant awards follow prestige, or might they be differently awarded and therefore compensate for what prestige otherwise gives?
So, Leisha, to answer your question, I have a camera here. To answer your question, we know that NSF has these programs like EPSCoR that try to give sort of more points to institutions that come from states where there's not already a ton of federal funding. However, what I would say is that if you actually look at what happens in spite of F-score, faculty at prestigious institutions tend to have more money around, either private money, money from endowments, but also federal grant dollars. Still, I haven't looked at the data myself, but I suspect that it's out there.
Great.
Thank you.
There are still some refreshments over there if you'd like to.